Hi, in this video, I'm going to teach you about what a standard enthalpy of formation is. All right, the symbol for standard enthalpy of formation, delta HF, is right here, delta HF. F means formation, and H, remember, is heat, because enthalpy is a kind of a way of calculating heat, or heat energy that's transferred. The little degree symbol at the top here means it's at standard conditions, which for thermochemistry is not 0 degrees C, it's actually 25 degrees C, or 298 Kelvin. Also, 1 atmosphere of pressure and 1 molar concentrations if you have to have concentrations. It's just a definition at the conditions that we measure these enthalpies at. Because when scientists go and tabulate all these numbers, we want to make sure that we're comparing apples and apples. So all the delta HFs in the reference book are going to be for standard conditions. So the definition of this is really important. Whenever you look up a enthalpy of formation, what you're doing is you're looking up what the heat energy is that's either added or released when you form a substance from its elements in their standard state. That's really important. 1 mole of substance from elements in their standard states. So what do we mean by standard states? We mean whatever state an element would be in if you went into the lab at 25 degrees C, and how much energy you would either get out or have to put in to form that from just elements. Now, a really important thing to note is usually we're not forming substances from their elements. This is a convenient fiction that we use in the thermochemistry chapter, because if we compare everything to their elements in their standard states, we can go and use Hess's law to add or subtract these enthalpies of formation in order to be able to get some sort of enthalpy for a reaction that we want that doesn't necessarily involve elements. All right, a really important point also is you're not going to find delta HFs for elements, because if they're already in their standard state, it doesn't take any energy to form them, or you don't release energy when you form them. All right, you're going to be given values either in the form of a table like this, or maybe they'll be given in sort of a prompt. And so if we'll look, a really important skill to be able to do is to be able to write the equations for what actually these numbers mean. So when we say the delta H of formation of NH3, we're saying that negative 46 kilojoules per mole, that's the energy released if NH3 happened to be formed from its elements in its standard state. In fact, 1 mole of NH3. So if we write the equation for the formation of NH3 from elements in its standard state, well, NH3 is made from putting nitrogen and hydrogen together. But you got to remember, Chem 1 understanding comes into this. Nitrogen in its standard state is a gas, but it's also diatomic, it's N2. And H is also diatomic, it is H2. So N2 plus H2 will make NH3. Okay, one way in which this is different from Chem 1 is the delta HF is defined as making 1 mole. So when we balance this thing, we need a 1 in front of that substance. And so we can use fractions if necessary to balance this. For instance, we're only going to use a half of an N2, and we're going to use 3 halves, or 1.5 H2, and then that's balanced. In other words, balance the equation and then divide everything by a number to make that NH3 to be 1. So if I did 2 and 3 and 2, I would see, I want that 2 to be 1, so I divide everything here by 2. It keeps it in the same ratio. Or you can just use fractions. All right. So this is the equation for the formation of NH3 from elements in the standard state. So we can see from the table that the heat of formation from this is negative 46 kilojoules per mole. So if you happen to do that equation, it will release 46 kilojoules of energy. That energy, remember, is whenever you make a bond, you're going to release energy. Whenever you break a bond, you're going to, that's going to require energy. So it apparently, the bonds that we make in this process we release more energy than we make in this process. So that's neat. If we look, NO2 has a value of 34 kilojoules. So apparently making NO2 from its elements in its standard state would be an endothermic reaction. And so if we wanted to write that process, we'd have to write NO2 as a gas, and we're going to create that from elements, so nitrogen and oxygen. And both of them would be diatomic, and they both be gases in their standard state. And apparently we only need half an N2. Half an N2 means half a mole of N2 gas. It doesn't mean just 1 nitrogen half. All right, and so that'll come out. And so apparently that's an endothermic process. All right, so I pointed out that all of this is a convenient fiction. So again, 34. We'd have to put in 34 kilojoules per mole. All right. All of this is kind of a convenient fiction. Because really the way in which we're going to want to use this is we're going to want to use this with Hess's law. And so if you look on this next equation, we're going to want to use that Hess's law equation that in any delta H that we want, we can add together all of the heats of formation of the products, and then we can reverse the sign, so negative, of all the heats of formation of the reactants. And when we add up all those numbers, we can get what the delta H for a reaction is. So if you look at this reaction right here, we can go and we can look up the delta H for all of these substances. Well, aluminum being formed from elements in its standard state, well, aluminum is a solid in its standard state. So the heat of formation of aluminum is actually 0 because it's an element in standard state. The F2O3, we can look up on the table on the previous page. So that's going to be negative 826 kilojoules per mole, maybe 826 kilojoules, right, per 1 mole. And then aluminum oxide is going to be negative 1676 kilojoules per mole, negative 16 kilojoules per mole. And then iron in its standard state is a solid, so the delta HF of that is going to be 0. All right, if there's a coefficient, we have to multiply these numbers because that would be for 2 moles. Remember, delta HFs are defined for 1 mole. But it looks like the only things that have coefficients in this equation have delta HFs of 0. So it doesn't really look like we have to do anything to there. So what we're going to do is just do the products. So when we do this reaction, it's going to release 1676 kilojoules when we make the aluminum oxide. It's not going to release any kilojoules to make the iron from iron. And then we have to flip the sign of the reactants. That's why we subtract. So we're subtracting a negative 826 kilojoules from breaking up that iron oxide. So you're going to, in other words, we have to put in its positive 826 kilojoules to break that up. And when we do that all out, I got to grab my calculator. All right, so 1676, it's a negative 1676, and plus 826, and that's going to be negative 858 kilojoules per mole. It's per mole of reaction. What that means is it's per reaction as written right here. All right, so that's how we can do it. Now, I want to point out that this equation that we used right here is really just a shortcut for writing all the heats of formation equations and then adding them up using Hess's law. So, for instance, what I can do So another way of getting the same answer would be to write all the heat of formation equations for everything here. So apparently to form aluminum solid from aluminum solid doesn't take any energy. That's why the delta HF is 0 for that. To form iron oxide, Fe3O3 solid, from its elements would be, you'd have to put in 2 irons, which are solid, and 3/2 of an oxygen, which is a gas. And that delta HF is that number that we looked up before. So that delta HF there is 826. So for the reaction as written right here, the delta HF of this is negative 826 kilojoules. In other words, we get energy out when we make bonds. Who would have thought? All right, then the aluminum oxide, if we write the heat of formation equation here, so this was a much bigger number. Apparently, aluminum bonds much more strongly to oxygen than iron does. It's 1676, negative 1676. When we form it from aluminum, atoms in their standard state would just be aluminum solid, Al solid, and 3/2 of an oxygen of another 2 gas, because that's oxygen in standard state. So that's the amount of kilojoules for that. And Guess what? To form iron from iron in its standard state is delta HF of 0. All right, so I mentioned to you that the previous example was just a shortcut for this. So now I have all the equations written out for the formation of all of these substances. And just like we did before, we would want to add up all those equations to equal the equation that's at the top here. So the way that we're going to do that is the same way that we learned how to do it. So we're going to circle everything. So aluminum is circled there, right? Rust is circled, aluminum oxide is circled, and iron is circled. And then to be able to add it up, well, aluminum oxide's on the correct side, iron is on the correct side, but we have to multiply this equation by 2, which, by the way, just pointing out, that would be 0, right? We would want to multiply this equation by 2. So that's also going to be 0. It doesn't matter. And we need to flip this equation because the iron oxide's on the wrong side. So we're going to flip this. And when we flip this, we do a plus there. Guess what? The math is exactly the same as the example we went over before. All we're going to do is add together the 1676 and the 826, the negative 1676 and the 826, and we get the same answer. So in other words, what I'm pointing out is that heats of formation, to wrap up, are numbers that are the heats that are released, the energy released when a substance is formed from its elements in their standard state. And if a substance is formed from the elements in the standard state, then we can write an equation for that if we need to, but a lot of times we don't even need to. We can just add up the numbers and remember, flip the signs of the reactants.